All right, so this is our array without anything in it. Now you can specify how large you want it to be. You can put parentheses on here and say I want it, 50 elements. It is parentheses because you're actually invoking a constructor when you do this. Like I said, vector is a template class. So that will invoke a constructor and it will set aside space for 50 integers. But you don't have to do that. You can just leave it like this. And then you have an array. And if you want to add something to this array, right now we've got nothing, but if you want to add something, we do array rr.pushback. And then you push back whatever you want. Now it has to match what you said was going in this thing. So if you said it was integers, it has to be an integer. But you can put an integer in there just like that. And we'll do a couple more. So there we go. I've got 3 integers in this array, and now I can treat it just like an array. So if I wanted to view one of those numbers, I can say R, and then I use my brackets with 0 because they start at 0, just like an array does. It might be more accurate to say element 0. And if we run this, we should see our 654, or my 654. You may have put something else. No. What? It's gone. Lost in the matrix. I'll just use that one. There we go. So it works the same, and you can modify it the same way. Like you would a normal array. And we use this in the SDL project, in the asteroids project, correct? So all of this should look familiar, but I'm going to go over it all anyways, just so it's fresh on your mind, and cover anything I may have missed the first time around. Okay, what's going on under the hood here? So if you look at the board, when we have an array, we know that we've got a section of memory, and it's set aside for this array, and all of the elements are right next to each other. And that's the rules of an array. It has to be that way. These all have to be the same data type, and they all have to be right next to each other in the memory. Then we can use pointer arithmetic, right? We can say, if we do have a pointer that's pointing at one of these guys, we can say pointer plus plus, or pointer plus equals something, and it will move over according to that math. And it doesn't matter what's in here. It could be integers, it could be objects, it could be pointers. It moves based on the size of whatever is in this array. And that's how an array works. And that's how pointer arithmetic works. Now, it may be that you have some other data right there. After this array comes a string or a float or some other object or whatever. So if we want to add one to this array, we cannot do it. This is why the array has to be set up at build time. We cannot just say, oh, I want to add another element, my array is not big enough, because they have to be all next to each other in the memory. And you can't just put it somewhere else, and you can't overwrite that other guy's information there. What vector does is vector gets around this, it works around it. It actually does set up an array, a real array just like this. So everything that works with an array works with vector. But if we do want to add something to it, what it will do in a case like this, if it doesn't have room for it, it relocates everything. You say, here I've got 6 elements, I want to add a 7th. We don't have room for 7 here, but hey, over here in the memory, I do have room for 7. And so it will section off this piece, and it copies all this stuff over. And then it will usually allocate a few extra so that you can grow a little more if you want to before it has to relocate again. But that's what it does, copies everything over, and now we can have our other one. And this all happens under the hood. You wouldn't know as a programmer or as a user that this is going on in your program. But it's something you, a programmer, should know, because if your array is really large elements and you're using a vector and you're growing it, especially if you're shrinking it, these are costly operations, all right? Depending on how much data has to be moved, that could be a lot of clock cycles if you're using a time-sensitive, or if you're writing a time-sensitive application, like a video game or a hardware driver, right? So that's what goes on. That's why vector can bend the rules. We can add to it and it can get bigger because it will do this. You can also remove stuff. So if I don't want this element, I can take it out. You can't do that in an array. In a standard array, this will, that spot is there. You can't just get rid of it. What vector will do is it will erase the information and then it copies everybody over one. Everybody scoots back. So it moves it all over for you. Again, that can be expensive, especially if you've got a really big array and you remove the guy, you know, up at the front. Everybody has to get shifted, and that's, you know, that can be expensive. It works fine, but that's what's going on under the hood. What else do we have here? Let's do a few more examples. Instead of just integers, we'll look at doing objects. Vectors are great if you do need a dynamic array and it only grows and then maybe it reaches a certain point and then it stops growing. That's fine, like maybe loading assets or something like that. You can load them all up at the beginning of your program. The array grows as large as it needs based on the database it's pulling from, and then it's done, it's set, and your program runs just like it was written in a regular array. So that's ideal situation. You kind of get the best of both worlds there. But if you're having to shrink it, or you're having to move around, or you're growing indefinitely, vector may not be a good idea. All right, so there's a structure for an item. I'll leave this here. I'll take out my cout statement. So there's one example. Let's make another one with objects. Vector. I want to put items in here, so that's what goes in the angle brackets. And we'll just call it items. Here's another thing I can do. I could specify, and when you specify it, sections off memory for that many items. You can also tell it what you want to put in there. You can say, go ahead and put the items in there. And you could, if I had constructors for my items, I could, take advantage of that. Now, it's worth noting, when you use this 2-argument constructor with vector, it copies this second argument. Whatever it is, it just copies it into all of these. All right, so keep that in mind. I don't have to push back any items because I've already filled it up, but I could. I've got 5 in there now. I can add another one and push back item. like that. And now I've got 6. Or I can say item, sword, can set the values and then push it back. And then I can just say items.pushback sword. As long as it is an item, I can add it. I can add it to my vector. And then just to verify that that does work, we'll do a cout. Item element 6. Items 6. And you can't print an item, but I can print the name. So I can use my dot operator there. All is lost. Well, I got 5. That gives me 0 through 4. This gives me 0 through 4.
So there's 6 now, right? So what was the last element?
Yeah, you're right. This is 5. There you go. That's wrong. Why didn't y'all catch me on that? Anyways, that works just fine. Okay, one more. Here we go. We can also do a vector of pointers. Lots of advantages to using pointers. One is if we do have to move our array, we're only moving integers. Even if this object is huge, you know, this object could be, I don't know, 200 bytes or something. But if we're just moving a pointer to it, we're only moving 4 bytes, 4-byte integer, that's fine. It's going to be a lot more efficient. And also, you get to work with pointers. So again, what goes in here is the data type. We want an item pointer, and we give it, we'll call it item PTR. Now, can I do this? Array of 10 pointers, yeah, that's fine. Can I do this?
No, because it's a memory location.
So what? What about that? Well, it's red, but why is it red? Hmm? Well, yeah, we said it was a pointer, so obviously it has to be an address. Can we do that?
Aren't they all going to be set to the same address?
Yup. You got one object and 10 pointers all pointing at the same object. Normally you wouldn't do this anyways. Normally you would want to do something like that. But you get the same problem there. It only makes one, copies all the pointers over, and you've got 10 pointers pointing at one object. And if you don't know that that is what happens, this can be a real nerve-wracking bug. Yeah, it only runs this line once. This is not a for loop. And then you will get, yeah, you get 10 pointing at the same thing. So this is typically not good. In fact, you may not even want to specify the size of this array. If you're using pointers, just tell it you want a pointer vector, and then we'll set up a for loop to fill it up. And then you would put, I want 10 in there, however many, I++, item, PTR, dot, pushback, not pop back, pushback. What did I do wrong? Nothing. IntelliSense is just dumb. And this will give you a vector of 10 separate items with separate pointers.
I have a question.
Yes.
What does pop back do?
We'll get there. Get there, one at a time. Okay, now if I want to display something in here, I can say element 5 or 4. Let's set it. Let's set that one. Item PTR. How do I set the name on item 4? I'll put my brackets. I put a 4.
3.
You said put a 3. I don't care.
No, because isn't it item 4 would be 3 because it's an array and it starts with 0? You want item 4?
Sure. Just yeah, it would be the fourth one. For the fourth one, we need element 3. But these are pointers, so we can't use the dot. Like if you try to do that, well, IntelliSense corrected it for me. I tried to put a dot in there. But yeah, it does have to be an arrow, so keep that in mind. And we can set it that way. There, we should see wine in the output. That works just fine. Okay, somebody asked, what does popback do? Pushback is a function. Popback is also a function. So we can do item PTR dot popback. And what that does, it removes the last element from the array. Now, what's wrong with this? Yep. I threw away the only handle I had to that object. It does not go out there and erase that memory for you or free that up. It just removes the pointer. So keep that in mind. That's a great way to create a memory leak if you're not thinking about it. Okay, what else can we do with vectors? It's important to remember that this is your data type. Vector of integers, or vector of items, vector of item pointers, whatever it is. And that way, if you want to pass it to a function, you can do that, and this is your data type. If I want to write a function up here, and I wanted to pass a vector of integers to it, then that's what you write. You write vector, angle brackets of integers, and then you give it a name. And you just think of this, even though it may look weird to you, you think of that as your data type. And then inside here, you can do whatever you would do. You can access it the same way, something like that. So this is how you pass a vector or any container. There's a handful of containers, so if you're passing a container, you pass it like this. What if you want to return it? Let's say I pass nothing. Inside here, I create a vector of something. I do some things to it. And then I want to send it back to whoever called this function. Then you're going to return whatever. And then it's flagging it because I said I return void. So how do I fix that? That's what I'm returning, that's what goes there. The same thing goes for a vector of pointers, a vector of vectors, anything like that. That is your data type. All right, any questions on the vector?
So since it uses up so much memory, when is it best used to use a vector versus an array?
When it needs to be dynamic. When you need it to grow and hopefully not shrink. If you're not, like pop back is fine. Pop back isn't going to cost you anything. But if you erase from the middle of it, then everything has to be moved, and that costs you. So if you were needing to erase from the middle of a vector in a time-sensitive program, again, like a driver or a video game, you don't want to use a vector for that. So how do we erase? Just in case you're wondering, what you have to do for an erase, there's some clever ways of doing this without doing everything I'm about to show you, but ultimately you need an iterator. And an iterator is just a fancy pointer that points to one of the elements in the vector. And it follows most of the rules of a pointer. You can do pointer math with it and things like that, but it's just made to work with the class a little bit safer. So if you want to erase from the middle, you're going to need an iterator. There are a few functions that return iterators. One of them is begin, and the other is end, and they return the first element, or an iterator pointing to the first element, and an iterator pointing to the last element. So let's set up one of those. Let's do it for this vector right here. If we want an iterator for that, we're going to say vector of item pointers, scope resolution operator, iterator. That's my data type. Give it a name, typically ITR in a closed scope. And then we have to set it to one of the elements, but you can't set it directly. You have to get an iterator returned. So we would say item PTR dot begin will give you one. So you can use that, or you can use dot end. And then if we wanted to remove or erase element 3, we're pointing at 0 right now. We can say ITR plus equals 3. I guess that would give us the fourth one. And then we can say item PTR dot erase and it needs an iterator. So that would erase the third one. Now, if you recognize that this is an iterator, can we just put that in there and do our math as well? So I can copy this and then add 3 to it. I believe that works. So then I would not need, I don't need that. Effectively the same thing, but I wanted to draw it out so you see what's going on. Any questions there? Again, we're only removing the pointer. If we don't clean it up, you got a memory leak. And if you wanted to wipe them all out, you can do that pretty easy with the dot clear. That will clear the entire array. There's a handful of other functions that you can use. Again, this would just create an enormous memory leak if you did not run a for loop and delete everybody first. So keep that in mind if you're working with pointers. You're just working with the pointer and the object you have to manage separately. Any questions on that? All right, let's take 5 and then we'll go look at some of the other containers. But if you're going to use the deck, you include it up at the top. We don't need vector for this. But that's what it stands for, double-ended queue. And you think queue, think like a line at the post office or the DMV or something like that. A queue is where things go in one side, they come out the other. So there's also a stack. I mean, there is a queue. Queue is a thing. Did I spell it wrong? Q-U-E. Yeah. There is a queue, you know, where you can add to one end, remove from the other. There is a stack where you add to one end and remove from that end. So you like stack up, think like a stack of CDs or something. Everything goes on top, everything's removed from the top. Anyways, if you want the best of both worlds, you get the double-ended queue. You can add or remove from either side. And the cool thing is it supports random access. So when I say random access, I'm talking about the array notation with brackets. I can specify whatever element just like I would with a vector, just like I would with an array. But I also gain the ability to add front, or like push front and pop front. So push front, push back, pop back. You can do all of those things with a deck. And you still get random access. So this is probably like the most advanced container of them all. And you use it the exact same way. You say deck, you tell it what you want a deck of. We want integers, we want items, we want item pointers. And it goes just like that. And it's got constructors and stuff like that if you want to use them, or if you're using pointers, you would do it the same way as before. And you can say inventory, pushback. We got pushback, and you see IntelliSense even pulled up push front. So if you want to do that, you can do it that way. New item. And this is kind of like what you guys did with your linked list. Remember, we could add to the front or add to the back, and the deck supports that as well. Vector does not support push front or pop front. Otherwise, the deck operates identical to the vector. You can specify inventory, whatever. Boots. It supports random access. That's what I'm doing right here. You can use it with a for loop. You can create an iterator for it. You can erase. All of it is pretty much the same. You just get the front and back. So what's the difference here? What's really going on? Why does vector even exist if we have this guy? So I'll show you how this one works. All right, so it creates an array just like vector does. And it will have elements, 0, 1, 2, and 3. And let's say it's right up against somebody else in the memory and we want to push back, or something on this side and we want to push front. What do? We already know vector copies everything over. The deck does not. It will go find new space for the new item. And it creates another little array right there. So if I'm pushing back and I want to add element number 4, it will be right here. And it creates a pointer that links these two together. If we run out of space again, it will do it again. We'll find another space in the memory. Set up a pointer for it. And it manages all of that under the hood. And you still get to use your random access. You can still say, hey, give me element number 6. And it knows where it is. Or if you want to push front over here, it shifts everything. Or it doesn't shift anything, it shifts the indices. We'll say, okay, this is now 0, and this is now 1, and this is element 2, and so on. And all that happens under the hood, you never know about it. But if it needs to grow, and it has run out of room, the big difference is, instead of moving everything to a new spot, it finds a spot, it sets up shop there, and it just ties them together with pointers. Yes.
So when you delete stuff, let's say you delete the, 8 and 9 over here, back end, will it delete the pointer and not have a memory leak, or will it still do have a memory leak?
If we delete 8 and 9,
like, yeah, 8 and 9, that one, let's say you back those two up and you only have up to 7 or whatever. Will it still keep it there, or will it delete that?
Is this something, if I erase these?
Yeah, if you erase everything on that part of the, let's say you add something and it makes a memory, and then you wanna back it up and it deletes it, will it automatically keep track of that, or will it cause a memory?
It's going to keep track of everything.
Even
Now,
the pointers it makes, that's what I'm trying to say.
yeah, you don't have to manage any of that.
Okay.
It's gonna take care of all of its own pointers and its own structuring.
So is there any advantage of using like vectors instead? Like efficiency wise?
Here's what you give up. If I have a pointer going to one of these elements, right here, if I just got, PTR pointing at that guy, and I say pointer plus plus, he goes right here, right? If I say pointer plus plus again, where does he go? He's gonna go right here.
Or whatever.
So you give up pointer arithmetic if you use a deck. Your iterator will still work right, because iterator is built into the deck, and it behaves like a pointer, but it will be smart enough to travel this way. But a standard pointer is not going to be able to do that. Within these small arrays, it may, if I erase one of these, it may scoop these two over. So there may be some of that still going on. I know just from like studying this, there's probably a whole lot more going on under the hood with the deck than there is any other container. But it also is one of the nicest and most flexible. But if you are just going to grow your array to a point, and then the array doesn't change anymore, you just use it, vector's better than this stuff, because this is a little more overhead. It does have to keep track of these things. But if it needs to be flexible, like this is the best of both worlds. This is a linked list of little arrays. So it is pretty cool. Just know that's what's happening there, and if you do try to use pointer arithmetic on it, you get some weird results after a while because the pointers don't know. But yeah, otherwise this all works the same with the advantage of push front. In the AI class, push front comes in really handy for pathfinding algorithms. If you've got a whole bunch of nodes and you've traced out a path and then you want that path back, if you push back, then your path is completely backwards and you have to reverse everything. But if you can push front, then your path is all in order and it works out really nice. So the deck is pretty good. And then the last one I want to cover is the list. And lists is a linked list. It is a doubly linked linked list. So in the linked list you made, you had a previous, or you had a next for every node. Every node had a next pointer going to the next node, and you could have had a previous pointer that would point to the one in front of it. This is the same thing. So with the list, you can make a linked list of anything, same as the vector and the deck. You can have pointers, integers, primitives, whatever. You can push front, you can push back. You give up random access. Why? Because we no longer have an array with the linked list. If you remember, with the linked list, everything just kind of goes everywhere. It does not try to structure it side by side in the memory like an array. It's just, it's got a node here. If you push back, it's going to add one, somewhere. Could be anywhere. We'll just add one to it wherever it finds memory for it. If you push front, it's going to add one on that end. Okay, this is probably the best for removing and adding to the middle all the time. So like if you want to cut that guy out, you can do that a whole lot easier than copying stuff over, or shifting it all around. You're just moving a pointer just like you did with the linked list. So this is a really nice, robust, built-in linked list. But you don't have random access, and that's the worst thing about it. If you want to work with this, you have to use an iterator. So for this here, I've got 3 items on my linked list. Wait, this doesn't work. You can set up an iterator. You can say list, item pointer, iterator, and we'll set it to the head or the beginning. So there's the head. There's the tail. Probably don't need both of those, but that's what those functions are. Begin and end are iterators to the front and the back of the list. And then you can use your erase or your iterator. Is that wrong? So think of it like a pointer. If I'm going to use my arrow, I've got to dereference it. So I get the object, and then I can use the arrow for this pointer to set the value. I think you do have to use parentheses on it though. Yeah. So dereference the iterator, and then use your pointer notation to access your members. This is not as bad if you're not working with pointers. I have to change all of that. No, I still have to use parentheses. Huh. Well, that sucks. But that's how it works. All right, any questions on the list? This is my least favorite container. I like random access. So typically I will use the vector, and if I need to, I will use the deck, and then, but sometimes you need a list. So if you're adding and removing constantly, I think of like a video game, like if you think of an MMO, where you've got players constantly coming into an area and then constantly leaving an area. So you might set up a list for something like that, because you don't know who's going, who's coming. You can always add to the end or add to the front, but the guys that are leaving could be leaving from anywhere. Another thing might be like a Discord server, right? You've got one server, you could have users coming and going at any time. The guy in the middle of the list might want to leave. A Discord server is not as time sensitive, so you can get away with using a vector on something like that, but this would be much more efficient. So stuff's coming and going whenever. A list is a better option than a vector or a deck, but more awkward to work with in my opinion. Any questions on the list? Okay, now we're going to move on to the forbidden zone. I'll show you how to make your own templates. If you want to do this, no, it's not just C++ magic going on there. Those are classes written by somebody, and they work the way they do from C++ code, but I'm going to show you, I'm going to scratch the surface of what's going on there. When it comes to templates, you can do all kinds of things, and it's kind of like pointers. You know, going up to pointers with some next level programming, and it seems simple at first, but it opens a huge can of worms. This is going to do that again. We're going to go one more level up in the craziness, and you're going to see just why C++ is so powerful, and then why after so many years it's still boss of a language. So here we go. If you want to make a template, you're going to write the word template. And typically you're going to put type name T. And then you can write a class, or you can write a function or a structure or whatever. Trying to think of a good example here. Let's write class hero. I'm going to make everything public. Okay, here we go. So what is T? No. What is a T?
Is that class? Class T?
No, someone said it. Type name. Think about that. What does that mean? It's whatever I want. Think about the deck and the vector and the stuff we just used. I could put anything in there, right? The same thing here. What you end up with now is variable data type. Inventory could be integers. Inventory could be items, could be item pointers. It could be any data type.
So it's kind of like an all-inclusive data type?
I wouldn't say all-inclusive, but it's flexible. It can be anything. You now have variable data types. That's what a template does for you. So if you think about that for a while, there's a whole bunch of madness that can come out of this. Just like pointers, it can go super crazy from here. We're going to keep it super simple though, and I'll show you how this works. We can do this the same way. I can create a hero, and I pass. Let's say I want inventory just to be chars. I can do that. and then I can say hero.name equals Fred, and then hero.inventory equals, you know, any character is fine. That doesn't make any sense. It's hard to come up with a good example for this where something can have a variable data type. But you see, that's how the vector works now. That's how the deck works. That's how we can create a vector of anything. It is a template class. And like I say, in a lot of places, like game development companies that use C++, template programming is forbidden because it just opens up a lot of, you can do all kinds of cool stuff with it, but you can also get really crazy and it can make your code really hard to read, really hard to debug. If you've got errors in your templates, the debugger doesn't work on those very well. I'll show you why in just a second. But these are really powerful, really cool stuff, but proceed with caution. Let's say char is not really great for this hero. Inventory of equaling z doesn't make any sense, so let's try again. I can do that. I haven't changed anything up here. I'm not going to either. But hero2 dot name works just fine, and inventory can equal an item. That's fine, or I can go. The item is already there. I can just name the item. And that works. And we can keep going with this. If we had a really complex program, we could do whatever we want in there. Up here in our template, we can write functions with this T. You can have more than one. You can have an array of T. If you wanted to do that. Is that crazy? But here's a really cool thing we can do with this template function. What if we want the array of inventory to be any type we want, and we want it to be any size we want? Well, you can also do that. So come up here to this template. I'm going to add int k. And I'm going to drop k inside my inventory box. And now I can create an array. Now when I create my hero, I have to specify how big I want the array to be. But here I can do 6 for my char. I have to treat it like an array now because it is one. So I'll have to add brackets there. And then here I can say 3. With that same template class, I have an array of 6 char, and I have an array of 3 items, and I'll have to treat it as such. But that works just fine. It's totally dynamic, and I can create another hero full of items, and maybe he only has 2 slots for his inventory, something like that. I'm not using a vector or anything for this. This is just how templates work. How does it work? We already said an array has to be defined in size at build time. So how do we get away with this? Anybody want to venture a guess? Okay, everything I said is still true, still has to be defined at build time. So with that stipulation in place, here's what happens. When the compiler goes to build this program, it comes up here and looks at all the template functions, or all the template classes. It says, okay, this is variable, this is variable. Where does the programmer use this template class? And it comes down here and it looks at it. It says here, we need one with t being a char, and that k is a 6, and this is what it does. It's going to copy this before anything is compiled, and it writes this function again. It will be slightly different name. Now you don't know that. It keeps track of it on its own. And we said, you know, t was a char, k was a 6, and now we have a class that represents our needs right here. This is okay, but down here it's a little bit different. So it does it again. Okay, t was an item, k was a 3, so it writes another class for that one. And now all the stipulations are met. We know the size of our array before we build, and we know the variable types, and so this works just fine. That's what the compiler does for you. The compiler goes out here and it writes this code for every time you have used that template class. It makes it specific for that use. And that's why the debugger has a hard time with these things, because you don't see this. Like, this is all under the hood.
Could this be like character creation? They all have this start with a certain thing, name, whatever, and then it's just a character being created, like a template? You make a template for character creation?
You could. Would you need to is the thing. What I've gained here is I've given these guys arrays that are different sizes and different types completely. And I'm not using inheritance either. This isn't through polymorphism that they're different. It's completely different data types. That's a primitive. That's a structure.
Yeah, like, because you have different species, different characteristics, different racials and stuff, but you're still just making a character.
The answer to your question is yes, but you would probably not use this for that. You would probably use inheritance for something like that. Anyways, that's how templates work on the surface. Now this gets deep and crazy, and I'm not going to go there, but there's a practical application for it, and it's pretty cool without getting too crazy. So there's custom templates.